Okay, good. Welcome to your next functional analysis lecture, and in particular, welcome to the usual way of spending the last hour before your weekend. So today, what we are going to talk about is a new chapter of the course, and that is weak convergence, and basically finally having some kind of solution for one of the major problems of infinite dimensional spaces. So that's the plan for today. So in our course, that's chapter 4. Weak convergence. And weak convergence, as opposed to essentially what you've been doing for all your life so far, and that was strong convergence, convergence in the sense of distance going to 0, so convergence in the sense of the normed space. Now, why is strong convergence? Well, nice, but just not good enough for life. Essentially, the strong convergence is too strong to guarantee that all sequences you want to look at in life might at least have a subsequence that converges. And that is usually the bounded sequences. So an important difference between, on the one hand, finite dimensional spaces and infinite dimensional spaces, where of course everything we do is always about normed spaces, is that in finite dimensional spaces you have the theorem of Heine-Borel, which tells you that if you have a closed and bounded set, that thing is compact. If you're over here, it tells you, well, in general, closed and bounded sets are not compact. In particular, balls, closed balls, are not compact. So what that means is that here is compactness is okay if you are closed and bounded. And on the other hand, here compactness is a massive problem. So we've seen one way of getting around this issue in an earlier chapter, where sometimes you have an operator which turns bounded things into compact things. So if you have nice compact operators, you can get around it by then talking about the behavior of these image sequences, and you might get some convergence. In general, this just doesn't work. We know that in particular a bounded sequence might not have a convergent subsequence. So what we have is xn bounded, then this does not imply that there exists a convergent subsequence. And now, depending on your mood of the day, you might be saying, oh, well, so what? Not another property that doesn't work out in infinite dimensional spaces. We should be used to that by now. We know that linear operators might not even be continuous on infinite dimensional spaces. We know that completeness might fail and all of that. But actually in practice, completeness fails just means you're having the wrong norm. Operators are being unbounded, that can happen, but a lot of operators are bounded. But here, completeness, like every infinite dimensional space that you want, bounded sequences just can't be guaranteed to have a convergent sequence. And that's a real problem, because if you think back to your analysis education so far, how often have you taken a limit of a subsequence? Pretty often. And one of the sort of first instances where this was really useful was in analysis in first year. So let me just recall one case. Sort of, where do we use that nice sequences, let me just put it that way, have convergent subsequences? For example, for the very basic fact that continuous functions achieve their max and min. So for example, that was analysis 1 or analysis 2. If f is from a bounded and closed interval into the reals, if that thing is continuous, then the max of f is achieved. How did we use that? Well, we said we can take a sequence of points in here that goes to the supremum, or that goes to infinity if the supremum doesn't exist, then because I'm a subsequence of a bounded interval, Bolzano-Weierstrass tells me there's a subsequence that converges, and then you converge to something that's your candidate for maximum, and continuity tells you the maximum is achieved. But to find a candidate that could solve your problem of finding the maximum, you need a way of converging. And that's exactly what goes wrong. And of course you could say, oh, well, that's one-dimensional only. What else do we have in real life? Real life is usually not one-dimensional, but the problem remains. So this is a sort of major problem in really practice, and practice depending on how practical you are as a mathematician. Practice. It could be whether you're an applied mathematician, you're someone who cares about proofs, is in really a problem in lots of situations. So why is that a problem? Well, many arguments go by something like iterations. Or they use that you're solving a sequence of easier problems. It's also a kind of iteration. What you do, for example, in numerics is you have a problem that's posed on an infinite dimensional space. You use a so-called Galerkin approximation to look on finite dimensional spaces, and you hope that thing has something to do in the end with the original problem. And then similarly also, a lot of situations you can't quite solve your problem directly, but you're considering basically a sequence of almost solutions. So solutions up to a little error term. And in all of these situations, that means you get some kind of sequence and often this thing is bounded in the right space. For example, because you a priori work on a space that's bounded, or because you have objects where the energy that you consider just shoots off to infinity. When you get really big norms, therefore minimizers will not be behaving like shooting off to infinity. Situations like that, boundedness is usually easy to establish. So then the big question is, can we somehow get some kind of convergence? And once you have some kind of convergence, you get some limit, and that limit is a candidate for what your problem is like. So it's not the end of it, but it's the first step, getting some convergence. And actually that works in surprisingly many situations. So we said before, in analysis in first year, you did this problem of achieving the maximum on an interval, and actually this basic principle of just following a sequence that gets close to the max, where the function value gets close to the max, is a really powerful method that you use nowadays really also at research level. So the generalization of this is what's called the so-called direct method of calculus of variations, where method doesn't mean I solve anything explicitly. You've all given up on that years ago, solving anything interesting explicitly, but it's a direct method of proving existence of an optimal state. And so most of the situations, optimal state means you want to minimize something. So in my life, I usually want to minimize energy or area or something like that of some nice geometric objects. So you might be looking at curves which have nearly minimal lengths under some constraints, surfaces which have nearly minimal area, things like that. Then what do you do? Well, the basic cooking recipe is as follows. So basically we want to find minimize. So we want to minimize some kind of E from a subset A into, say, if it's an energy 0 to infinity, where A is a subset of the right Banach space, where your quantity makes sense. Now, what's the natural thing to do? Well, you're just going to take exactly what you did in 1D. So you're going to take xn in A, so that the energy of xn tends to the infimum of the energy over A. So that's bounded below by 0, the infimum exists. Doing that, you hope that these xn's behave themselves. So you hope in particular that xn is bounded. And that's often the case because usually energies are really, energy don't like objects which have huge norm because they're usually shooting off to infinity. So a typical energy, just to make a 1D example, typical energy is something like a half t squared. That's just an energy in 1D. A typical energy of a function, and my personal favorite energy, is integral of gradient of u squared. So where u goes from a domain into the reals. That's the so-called Dirichlet energy. And so, of course, if you have lots of gradient, that's just really bad. So often things have norm shooting off to infinity if you take the right norm. So that's what you hope. And then in the next step, you hope that this means that xn has a subsequence that still converges, in some way to some x star. And then one more step, you show that x star is still a guy that you care about, an admissible object, and you show that actually the energy of x star is equal to the min. So this is all the basic level hope, but the things which you can basically do exactly the same as in the 1D case is showing something is bounded. If you have a nice energy, that will be fine. So for example, the thing we had here, if you go A, B to R, continuous, that's good enough. Or you could also say, if I have f from R to R, with a property that f of x goes to infinity, when x goes to infinity, then that's one of the things, sorry, minus infinity, that's one of the things you proved in your first year, that this achieves the max. Or if I go to plus infinity, it achieves the min. So these things work. So usually those things are quite good. And proving estimates works. That thing has to do with, is a limit still in the set where the objects are in? So this property here has to do with, is A closed? Often when you set things up the right way, that still works. This is x star equal to min, has to do, does E of x j, does that actually converge to E of x star, i.e. this has to do with continuity. And so all of these things for nice problems can be solved. So the big question is, does this still work? And this has to do with compactness. And this is the point where the standard methods just break down. You won't get compactness in the usual way, but we're going to see that if we relax what we think of convergence and accept something weaker, then this bit still works. And it still works in all of your favorite Banach spaces, not in the scary ones. So favorite ones are reflexive spaces, for example, or also you could do things in dual spaces of separable spaces. Scary spaces are things like L1, L infinity, and those guys, they are what we do doesn't work. But in everything else it works. And actually this is exactly how you would, for example, show that a thing like that has a minimum, say in the set of all functions where you prescribe boundary values. And once you can do that and you have your right spaces, you can finally prove that the PDEs you analyzed last year actually have a solution. So the existence of solutions of PDEs can be shown using minimization methods like that. Okay, so that's supposed to keep your motivation up for the rest of the lecture. Now we jump into what do we actually define and why does it make sense. So part 1 is just definition and examples. So to define things, let's think about how could we try and define convergence. So previously we had always convergence if the distance between the object goes to 0. So that really means I compare two objects in like infinite dimensional spaces directly with each other, and I pretend I can actually measure their distance properly. Now another way of thinking infinite dimensional spaces is, here's my infinite dimensional space. I can just sort of look at it from one direction and look at scalar valued objects, scalar valued functions that assign to each object a function value. So instead of thinking of the objects themselves, I can think what happens if I throw an element of the dual space on my object, what value does this give? And so one thing you've seen is as a corollary of your favorite theorem from last term, namely Hahn-Banach, or if it's not your favorite, it should be, because it's the most useful one you learned back then. So a corollary of Hahn-Banach tells you that for all x, y in a non-space, we have x is equal to y if and only if looking at the images of x and y with continuous functionals gives you the same. So if and only if this holds for every f in the dual space. So you could think, oh well, that's a nice thing about individual objects. Now you need to be careful, this only works when the objects are fixed. It doesn't work for convergence. So the first warning is not, the analog is not true for convergence or sequences and convergence. So what we know is that if xn converges to x, then this implies that f of xn converges to f of x for every single f in x star, as such f are continuous. And therefore, of course, convergence gives you that. But this statement does not imply this. So you can think of this being a strictly stronger statement of convergence. So here, of course, that's norm convergence. Norm xn minus x goes to 0. Then this thing over there, and then mathematicians are very creative when it comes to naming things. So the strong thing we call strong convergence, and the weak thing we call weak convergence. And so everything you've seen so far was strong convergence. And now we just take this thing, this consequence of strong convergence, and say if the xn's just satisfy that, then that's what we call weak convergence. So the main definition of this chapter would be the following. So we have x a non-space, and we have xn sequence. Then we say that xn converges weakly to some x in x if exactly that thing holds. So for every way I'm testing, for every way I'm taking like a one-dimensional picture of my sequence, it looks like it converges. So for all of those, I have f of xn converges to f of x. Now, whenever you define something and you call it weak convergence, you should check that it's really weaker than what you call strong convergence. So here, that's okay. Another thing you should do is introduce notation. So what notation do we use? So The type of notation I would suggest for this depends on the quality of your handwriting. So if you're like me and whose handwriting is sometimes a bit dodgy, put a W on top of a half arrow, because otherwise your arrow might look similar. Shorthand, if you have very good handwriting, you can also just write this. So half an arrow is weak convergence, full arrow is strong convergence. Okay, so let's start with some examples. And let's start with some examples where essentially your sequence looks like it converges. If you always look at least, say, certain domains when you test, but it doesn't converge in norm. So the easiest example would probably be in a sequence space. So let's take L2 of C, and let's look at sequences that eventually are just constantly 0 in each component. Then that's pointwise convergence, but actually we can also have sequences like that which converge weakly. So I can, for example, take En, my standard basis, so En at the jth interval is just delta Jn. And now I claim this standard basis, this just goes to 0. So En goes to 0 weakly, but of course En doesn't converge to 0 strongly. So how do we prove that? This is, well, okay, as the norm of En minus 0 is just 1, and 1 doesn't go to 0. So we definitely don't have strong convergence. Similarly, you can make an argument that that guy definitely doesn't have a convergent subsequence. You have the same issue all the time. It would need to converge to 0 because it goes to 0 component-wise. Any other guy, therefore, doesn't have a chance of being the limit, but 0 is also not okay. How do we prove weak convergence? Well, our theorem, our definition tells us we need to take an element, just any element of the dual space. We need to check what happens and hope it goes to 0. So when you're in L2, this is really nice because you're in a Hilbert space. Therefore, you know exactly what a dual space is. It's testing with elements of the Hilbert space and seeing whether that goes to 0. So let's do that. So for all f in L2 star, we know that there is an element y in L2 such that applying f to a sequence x is nothing else than summing up xj, yj. And so therefore for us, if I now plug this in, I have f of En. This just gives me the sum of yj, Enj, which is a fancy way of saying this is yn. And so f of En just gives me this one yn, this one component. And of course, that needs to go to 0 as n goes to infinity, as y is an element of L2, so the sum of the yj's is finite. So therefore, this goes to 0. Here you already see why L1 is a problem, because when you have L1, the dual space is L infinity, and then that last step causes you trouble, because a sequence in L infinity is just bounded, but doesn't have components going to 0. So this statement is wrong in L1, and actually L1 is a really, really weird space, because L1 doesn't care whether weak or strong. Little L1, it's just the same. Which in practice is really bad news, because we said we need a different notion of convergence. You have the same, so it has the same problem. So it's not a good thing. So this is for sequence spaces. You can now do the same thing for function spaces. So let's have another example. Let's go to your favorite function space, which is of course big L2 over some interval, or at least my favorite function space is big L2. So what could go wrong in L2? Let's go for a sequence which doesn't have a chance for converging, because again, the thing it would need to converge to is 0, but it can't do that. And you can build that in various ways. So we can, for example, get Gn to take something which concentrates a lot. So I take 0 to 1 over n, and I scale it up so that it has unit length again, unit norm. So I need to multiply with square root of n. So then the norm gn L2 squared is integral of square root n squared from 0 to 1 over n, which is a nice 1. So therefore, that definitely doesn't go to 0. At the same time, these gn's go to 0 almost everywhere. So any limit that has any chance, any function that has any chance of being a limit would need to be the 0 function. Therefore, we have no chance of converging. But that thing converges weakly. So my claim is Gn goes weakly to 0. How do I prove that? Well, I have to start again with an element of the dual space. So let me just call it T, an element of the dual space. Again, you know how to write elements of the dual space. They're inner products with a fixed element. So here, integral with respect to a fixed function. There exists we have G, so f in L2 such that T applied to a G is given by integral f times G. So now we hope that some integral here goes to 0. So let's see. So what do we have? That Tn of T of Gn equals integral of Gn times f. And now we want to somehow bound that thing. And then bounding by something that should please go to 0. And now in L2, what's the reasonable thing to do? Estimating stuff, probably Cauchy-Schwarz. Exactly. If I had LP, reasonable thing to do would be the general version of it, Hölder. The one thing you shouldn't do is to try and use Cauchy-Schwarz directly over R, because that's a bad idea. So I could do that. Let me just do the wrong thing for a moment. I could do Gn times f, and I could just bound this with integral f squared over R to a half integral g squared to a half. But that would be fixed. That would be 1. That would be useless. But if we did that, we completely would ignore just how does that function look like. So because my function is really concentrating inside a tiny domain, everything else that happens outside the domain, this functional can't be bothered to even look at it. So this functional completely doesn't care what f does on most of R. But if you do an estimate like that, you would take into account the function values on all of R. And that's just a really bad estimate. So let's get rid of it immediately. So the only slight trick I need to make is to say, well, I can integrate over R, but honestly, the thing is defined on 0, 1 over n, and everywhere else it's 0. So I can just as well write it that way, as integral from 0 to 1 over n. And now we can Cauchy-Schwarz it, because now I get the f on a tiny, tiny interval. That should be pretty small. So I bound it with Cauchy-Schwarz, and I'm getting integral of fn squared from 0 to 1 over n to the half, which is just a 1. And then I'm having the integral of g squared 0, 1 over n to a half. And now I'm okay, because this is just a fancy way of writing integral of g squared, which is an integral function, times a function that shrinks down from 0 to 1 over n to a half. And now, of course, this function here goes to 0 almost everywhere. And importantly, it's dominated by g squared itself. So this goes to 0 by our dominated convergent theorem. So that's a typical example of a weakly convergent sequence. So weak convergence doesn't care if stuff sort of shrinks in, because if you look at your object, it's a sort of, you don't see that. Now, what else could you do in L2? So we had this case where we have concentration, as you call it. We could also do something else. Instead of concentrating, we could oscillate and have something really behaving quite wildly. So another example would be, I look at Gn, which is something like maybe here 0, and I'm going to go from +1 to -1, more and more. So I can build a Gn like that by adding up characteristic functions. So I can take my Gn to be, for example, the sum j is 0 to n minus 1. I take the characteristics on the first interval. Let's say I go up first in 0, and then I stop at 1 with this oscillatory behavior. So I go for the characteristic function on 2j to 2 over n to 2j plus 1 to 2 over n. And then I subtract the extra thing, j is 0 to n minus 1 of moving the 2j plus 1 over 2n, and then 2j plus 2 over 2n. And if you want open intervals or half open, that's also fine. It's only defined almost everywhere anyway, so that won't make a difference. What do you think does that thing do? Does it converge to something strongly in the standard sense? And does it converge weakly? So you can think, then I can do my little board cleaning. Strong convergence? No, otherwise I wouldn't mention the thing here, right? Wouldn't make sense. And actually, I mean, how could it converge strongly to anything? It would basically need to be the function which is 1 and minus 1 at the same time. That makes absolutely no sense. Weakly convergent? Probably. Wouldn't mention it otherwise as well. What should it converge weakly to? Only reasonable thing? 0, exactly. And a thing like that always converges to the average weakly. So this thing actually, Gn goes to 0 weakly. And this is a nice exercise for you. If I put weights here, then it will just go to the weighted average. And that's the general feature. Weak convergence just averages things out. And morally speaking, you integrate against the test function. So the plus and minus bits sort of cancel out. At least if you test with a function which is continuous, then you can prove it nicely. Otherwise, you need to work a bit harder. Okay, so that's another thing that can go wrong. And then let's do a final example. And that's really sort of the final feature that can go wrong for LP spaces. And that's it. I can either concentrate, it oscillates, or it just can't be bothered hanging around and it shoots off to infinity. That's the other thing which can happen. So if I take Gn is the characteristic function from n to n plus 1, then this thing again converges weakly to 0, but it certainly doesn't converge strongly. And again, it's basically, if I look at an interval f times Gn, then this thing only cares about an interval that gets further and further out there, but the f will not have a lot of interval left out there at infinity, so the thing just goes to 0. Okay, so that's basically examples. Now, all of these examples you might have spotted, I always went for something that had norm fixed, or at least norm bounded. I never tried to do something where the norm was actually shooting off to infinity. Even though, well, why not? Why not looking at an example with a question mark, which already tells you it's not going to be an example, like maybe a sequence xn is n times en. something like that. Something like that will not converge weakly. And anything I put here, even if I'm really, really quite n to the 1 over n, no, 1 over n is a bit too much, but n to the 1 over 2024, the creative one again, even that one still doesn't converge weakly. You can go off and you can check it and prove it, or you can just wait until we prove the next lemma or the lemma afterwards, which will tell us that weak convergence is one of the nice things you know from analysis 1 again, namely that convergence gives boundedness. And that still works when you have weak convergence. So that's one of the things when you define a convergence, that's quite nice to have. The other thing when you have convergence, and unless you like dealing with really abstract things, if I converge to a limit, that limit better be unique. And so the next thing we prove is that the thing we consider is actually reasonable in the sense that it has these two basic properties of convergence, uniqueness of limits, and convergence implies boundedness. Actually, I've lost my notes anyway. I haven't looked at my notes, so I should just not use them. I think that might be more efficient. Yeah. Okay, so let's go for part 4.2, and let's start with basic properties. And then later, once we have the basic properties, we also go for a theorem, and this is the theorem of Mazur. So we'll have one lemma, one proposition, and one theorem, so properly balanced. So let's start with the easiest one. Lemma, this is 4.2, which is uniqueness of limit, which is just saying that the limit is unique, i.e. if xn goes weakly to an x, and xn also goes weakly to an x twiddle, then x and x twiddle need to be the same. The proof of this, we've already basically seen the key ingredient in here, sort of on the other side of the board, is that if I had two guys which were different, I could distinguish using linear functionals. So let's do this by contradiction, and let's assume that x is not x twiddle. Then by a corollary of Banach, there exists an f so that f of x is not equal f of x twiddle. But of course, f of x twiddle is the limit of f of xn by definition. Same for f of x. And we have our contradiction. So it's just this fact, because linear functionals can distinguish between individual elements, the limit needs to be unique. So that's the first bit of good news. Let's get to the second bit of good news on boundedness, and a little bit more than boundedness. So let's upgrade from lemma to proposition. So proposition 4.3, which first of all, let's assume that xn goes weakly to some x. Then we have two properties. First of all, the xn need to be bounded. And secondly, the norm of the xn should have something to do with the norm of the limits. Now, what statement is reasonable? When you had strong convergence, you know strong convergence means the limit of the norms is the norm of the limit. Weak convergence, forget about it. We had lots of examples with norm equals 1 going to a limit which has 0 norm. So we certainly can't expect equality. But what happens is that whenever you have weak convergence, your norm can drop potentially, but it can't increase. So the second part is the norm of the limit, and let's maybe call this x infinity, looks prettier, is less than or equal to, you would like to write lim here, limit, but of course you can't even expect the limit to exist. It's a lim-inf in general. So for example, if I just go for a sequence xn, which is 0 for n even, and then one of the fn's for n odd that we just had before, that would be a perfectly fine sequence which converges weakly, because the two subsequences converge weakly. So all of that stuff still works. And of course here the norms would oscillate around. So what you want is that it's less than or equal to the limit. Of course it's also less than the lim sup, but that's a weaker statement. So how do we prove this? Well, the first one is suitable for Friday afternoon, because that's pub time. This thing follows from principle of uniform boundedness again. And so how do we use that? How to use the principle of uniform boundedness? So let's recall this guy tells us that if Tn are operators from some space y to z, where this should be nice and complete, so we want Banach spaces, then if Tn is uniformly bounded, if Tn is pointwise bounded, i.e. for every x the sequence Tn x is bounded, then it's uniformly bounded. So the norm of the Tn, this thing is less than or equal to m for some m. What does that have to do with functions, with functional? So the Tn are supposed to be bounded linear operators, but we have a sequence xn, which is just in a Banach space. The good news is whenever you want to view elements of a Banach space as some kind of bounded linear operators, you just need to throw two stars on it, go to the bidual, and think of them as functionals. And that's exactly what we do. So we use this, and we use that the canonical injection which takes an element of x, maps it across to x star star, which is a fancy way or a simple way of writing the space of bounded linear operators from x star to the field. So as usually can be R or C, that's fine. So we look and we identify elements in here with elements in here. So that way always works. You can't always identify a guy from here to here with one here unless you're a nice space, and then that's again unless you're reflexive. But if you're here, I can assign x to, let's call it iota x. So this is my iota, and iota x takes an element of x star and just maps it to f of x. And so this is a really nice thing, this canonical injection. We know that this is an isometric. So we know, and just for the fun and a bit of diversity in lecture, why do we know it's isometric? By corollary from Banach again, right? That's where this came from. So now we have a way of viewing elements in x as elements in x star. Therefore, we have a way of using uniform boundedness principle, and therefore we should be able to get it done. So what do we do? So given my, oops, let me just keep this here, move across. So given your xn's, you want to say you can identify it with operators. The norm doesn't remain, it doesn't change. Therefore, if you can prove that the operators have bounded norm, so will the original sequence. And therefore, you're going to be fine once you have checked that you have pointwise boundedness. And so really what weak convergence actually is a fancy way of saying if I take an element of my space, put it across into the bidual, that thing is a pointwise convergent sequence. So let me note that xn goes weakly to x if and only if fxn goes to fx for all f in x star. And so writing this as iota xn of f, of f, I can then just say this is equivalent to iota xn goes to iota x in quotes pointwise. So not convergent in the sense of non-spaces, but really f, throwing that in, that converges. And of course, pointwise convergence implies that they're pointwise bounded. And now we're done. So therefore, by the principle of uniform boundedness, I get that the iota xn are uniformly bounded, i.e., so what that means is there's a m, so that all the norms iota xn are less than m, but this is the same as the original xn. So we're fine. So we just had to translate things, and then we're okay. Okay, so that brings us to the final bit that we claimed. So the final bit is the difference, the estimate of the norm of the limit bounded by the limit of the norm. And so let's prove this as well. And just, again, for the fun of it, let's use another, or the same again, corollary of Hahn-Banach. So we know that by Hahn-Banach, or corollary of Hahn-Banach, by the way, it's always the same today. Next time we use a different version of Hahn-Banach. So by corollary of Hahn-Banach, there exists a functional f, which is in x star, which has norm equals to 1, which gives you back the norm of x infinity. So that's something you can prove. So using this, I can just use exactly that f and the weak convergence. So I get x infinity is f of x infinity is limit f of xn. And now each of those guys is bounded by operator norm of f times norm of xn. The operator norm is 1. I have no idea whether those guys converge, but the limit of the thing that they bound is definitely less than or equal to the lim_inf. So therefore, this is less than lim_inf, norm xn. And so norm inequalities, upper bounds on norms are preserved. And what that really means is a fancy way of saying, or a geometric way of saying this, is that if my xn's all have norm bounded by the same number m, so does the final x infinity. So a different way of formulating this would be, just need a little bit of space to draw this and to finish with the picture for today. So what we know is if xn in particular is less than m for all n, then also x infinity is less than m, i.e. if the xn live in a ball with radius m, then also the x infinity lives in a ball. So what that says is that if I look at closed balls, I can't drop out of the ball using my new notion of convergence. So that means balls, closed balls in standard way, are closed with respect to weak convergence. And this is the full balls. Never try to claim a sphere is closed. Because we had lots of examples where the norm was 1, but they converge to something which is in the interior of the ball, namely to the zero element. So it's not so much about the standard closedness, but it's about the geometric properties of a ball, and what's special about a ball that a sphere, for example, doesn't have. A ball is a convex set. If I connect things, I'm certainly not dropping out of a ball. And what we're going to see next time, that's the theorem of Mazur, is that whenever you have a convex set, then this is still okay. So if you have a convex closed set, then your limit, your weak limit, will be in the set. And so that's the plan for Tuesday. And now have a good weekend.